Pedram?
Yes.
Oh, hi. Our next speaker is Pedram Hassanzadeh. Okay, let's see if sharing works.
Okay, so do you see the full screen?
Yeah, I think it's showing. We can see also your cursor. So
Oh,
I'll send you a private message when you hit the 20-minute mark.
I might not be able to see it. Just just stop me and just tell me when.
Oh, yeah.
Yeah, that would be fine.
Okay, so Pedram will be talking about data-driven superparameterization for weather climate modeling using neural networks and transfer learning.
Okay, great. Well, first of all, I'd like to thank the organizers for making this session to happen despite everything that's going on. And I'll thank all of you for being here this Friday afternoon or evening. So today I'm going to tell you about some work that we have been doing on using deep learning to improve the modeling of subgrid scale processes for the ultimate applications to weather and climate modeling. First, I'll talk about data-driven superparameterization, which is a method we have developed in which we took the framework of superparameterization, which has been around for a while, and superparameterization has been shown to be more accurate than parameterization for many problems in weather and climate modeling, but computationally, it's a very demanding framework. So what we did, we used deep learning to do part of superparameterization data-drivenly. So we reduced the cost of superparameterization without losing much of its accuracy. Also, I'm going to talk about this problem of generalization or extrapolation when we train a neural network, for example, for data-driven parameterization or superparameterization on a set of data from a given system, and then we want to apply this to that system, but when some of the parameters have changed, for example, the forcing on the system might have increased. And I'll show that, well, these methods do not generalize well, but then transfer learning can be used to overcome that problem. So weather and climate modeling, as you know, it's a challenging problem. Part of the challenge is that we are dealing with a spatio-temporal, multi-scale, multi-physics, high-dimensional chaotic system. The multi-scale component on its own, it's a major source of challenge because computationally we can't afford to resolve all the scales. Just in the context of atmosphere, we know that we are dealing with many processes that have various smaller scales and are very fast, scales of a few seconds or a few centimeters, all the way to processes that are at scales of tens of thousands of kilometers and time scales of years, decades, and even longer. Even though mainly we are interested in what's going on at the larger scales, because all these scales are non-linearly interacting, we can't ignore what's going on at the smaller scales. For the purpose of this talk, I'm going to introduce three sets of variables, X, Y, and Z. X represent collectively the large, slow variables. Y represents the small, fast variables, and Z represents the very small, very fast variables that are usually hard to observe, and their physics, the governing equations might not be very well understood. Again, we are usually interested in the variability of X. We are interested in predictability to predict X, but we can't ignore Y, and in some cases, we can't even ignore Z. So the common approach to problems in climate weather modelings or engineering turbulence is that we use some low resolution models to resolve the large scales. For example, in weather climate modeling, we can solve some form of the Navier-Stokes equations at a low resolution that has a grid spacing of few hundreds of kilometers, or in some cases, tens of kilometers. Now, somehow we have to account for the processes that occur at the smaller scales below the grid spacing. And these are called the subgrid scale processes. And for these, we still know something about the governing equations. Sometimes we fully know what the equations are. It's just computationally, we can't afford to solve for them. Now, the most common approach is physics-based parameterization. We find a function P that tells us what's going on at the smallest scales if we know the resolve the scale X. And this idea has been around for a long time. There has been a lot of work to make parameterization better, but it still is far from perfect. So in the past 2 decades, in the climate community, there has been a lot of interest in a superparameterization approach. The idea of superparameterization is that we still solve for X at the low resolution grid, and inside each grid point for X, we have another set of grid, a high resolution grid, and we solve maybe the simplified versions of the equations of Y. And by simplified, for example, for cloud modeling, people, instead of doing 3-dimensional simulations, they just do 2-dimensional simulations to reduce the cost. Now, superparameterized models have been shown to do much better than parameterized models in capturing some aspects of climate variability and extreme events. But as you can imagine, superparameterized models are much more expensive because inside each grid point that is used for low resolution parameterized models, we have another set of high resolution grids, smaller time steps, and that we have to numerically solve the equations. And the reason that superparameterization in terms of accuracy does better, well, instead of finding some static function P, we are actually solving some form of the governing equations, and we account for the transient response in Y. So we are not going to assume that there is quasi-equilibrium between X and Y, which is a problem of parameterization, and that's something that I'm going to come back to it later. So these have been the most common ideas that have been used for weather climate modeling. And in the past few years, there has been a lot of interest to see how ideas from machine learning, artificial intelligence in general can be used to improve subgrid scale modeling. So one idea that most papers have focused on is to come up with data-driven parameterization that I'm going to call DDP from now on, where the idea is that instead of finding a physics-based function, here we replace that with a neural network or some other machine learning technique that we are going to learn that from the data. And there have been a number of papers looking at most convection in the atmosphere or ocean eddies, and the results are very promising, although there are some major challenges that have to be addressed. So what we have done in the past year or so is to think that, well, what else can we do going beyond data-driven parameterization? Can we use some of these advances in deep learning to actually reduce the cost of super parameterization? So what we are going to do, and I'm going to show you the results using a Lorentz system as the testbed, is that we are going to take the expensive part of super parameterization, which was solving these equations for a smaller scales at high resolution grid with a small time step, and we are going to do this part data-drivenly using a recurrent neural network. So as the testbed, we are using a multi-scale Lorentz 96 system. So in this system, we have equations for large scale X. X is a vector of 8, of size 8. F is the external forcing on the system. We have used F equals 20 to make the system pretty chaotic. Now for every component of X, there are 8 components for Y. So we have 64 equations for Y that depends on X, and it depends on Z. And for every component of Y, we have 8 components for Z. So in total, we have 584 ODEs and variables in this multi-scale Lorentz system. We can solve these equations, and just to give you an idea about this system, this is basically the spatio-temporal evolution of X, showing on the Y-axis. Here, X-axis is time. But in this talk, I show time in terms of model time unit, MTU, which is around 200 time step and 4.5 Lyapunov time scale. So if you look at the time series of X, Y, Z, X has large amplitude and low frequency variability. Y has an order of magnitude smaller amplitude, and it has high frequency and intermittency. And Z, it's even a smaller in amplitude, and it has high frequency variabilities. So we have a system with 3 basically level of spatio-temporal variability and a scale in this system. So in a paper that we published earlier in NPG, we look at the 2 ends of what you can do in terms of solving this system, predicting what's going on in this system. So one idea is that I just solve all these equations at the lowest, the smallest delta t that I need to use. And I'm going to call this just direct numerical simulation, or DNS. On the other end, we have a fully data-driven approach. Because we are mostly interested in X, we wanted to know whether we can come up with a trained, basically data-driven model that we train it on the past observations of X without knowing anything about Y and Z. And then starting from an initial condition in X, can we do some prediction on X? And in this paper that is out in NPG, we compared 3 type of methods. One is reservoir computing or echo-state network. We also look at an LSTM, which was mentioned in the first talk. So LSTM and reservoir computing, they are both recurrent neural networks. Also, we looked at a feed-forward artificial neural network, or an ANN. I'm not going to go through these results, but we found that some of the RNN, some specific architectures, can actually do a pretty good job in doing data-driven prediction of this multi-scale system. So just to show you an example, here the top panel, this is the DNS. When in this talk, DNS, we treat it as the truth. So this is from the DNS. The second panel, this is prediction using reservoir computing. It has been trained on data before t=0. So everything from t=0 is free prediction. And if you look at the difference, we'll see that for 2 MTU, or around 400 time step, or 9 upon of time scale, we have done actually a pretty good, fully data-driven prediction of this chaotic system. Now, if you're interested in fully data-driven prediction, some of these results can be interesting to you. But we were thinking of, well, what can we do with this? Practically what we have done, we have integrated some of those equations data-drivenly for like 400 time steps. Can we use this and apply this to make super parameterization cheaper? And that's the main idea that I want to talk about for the rest of this presentation. So kind of using these cartoons to tell you about what is the general idea of the different methods that we are building and their cost. So back to DNS, the DNS, we are solving all these ODEs and just counting the number of equations that we have to solve numerically at what time step. We have normalized the cost so that the cost of DNS is 1,000. And what I'm going to show you for the rest of this talk, these are all in this paper that is in revision at James and is available on arXiv. So this is the method based on DNS. We can also build a parameterized low resolution model. So here we are just going to numerically solve the equations for X at the time step of 10 delta T. And we use some sort of physics-based parameterization. We have actually used a stochastic parameterization from this paper by Torns et al. To parameterize the effect of Y. Now here we are only solving 8 ODEs, and the normalized cost of this is 70 times lower than DNS. It's just 1.5. Kind of going along with the idea of now what machine learning can do, we can do data-driven parameterization, or DDP. So here we are solving the equations numerically for X at the time step of 10 delta T, but we replace this P with an A and N. So again, here we are just solving 8 ODEs numerically. And in this talk, we are assuming that a trained neural network has 0 cost or negligible cost compared to a numerical model to run. So the cost of this is going to end up to be the same as the low resolution parameterized model. So I should emphasize that the LR model is really, this is the models that we are operationally using now, like the CAM or any other model that are low resolution models and parameterized. The models here, these are sort of the models that many groups have been trying to build to replace the physics-based parameterization with the data-driven parameterization. Now, going along of just using this simple system to show some of these ideas, we can also build a super parameterized model here. So we are going to solve the equations for X numerically at 10 delta T time step. And we couple this with another solver that will solve the equations for Y at a higher resolution at the smaller time step of delta T. Now here we have to solve 72 ODEs, and the normalized cost of this is 110. So this is pretty much the super parameterization philosophy. Now, the method that we introduced is data super parameterization, in which it's pretty much like super parameterization, except that what's going on in here, which is the integration of the equations for a smaller scale, we do that data-drivenly using an RNN, building on the results that I showed you earlier from our first paper. So here, because we are not numerically solving any equation for Y, we are only numerically solving 8 equations, and so the cost of DDSP is much lower than the cost of SP. So it's the same as the cost of LR or DDP. So these are the different models that we have built, and we are going to compare their accuracy. In terms of short-term prediction, we have also looked at how well they reproduce the PDF of the system and the long-term statistics, but we generally found that doing short-term prediction is a harder problem. So I'm showing you the results for short-term prediction. So here on the y-axis, we have the prediction horizon, which we defined as when the prediction error reaches 30%. And here, these are data points are averaged over 100 randomly initial conditions. So here we have the cost of super parameterization, data-driven super parameterization, low resolution model, data-driven parameterization. We also did a fully data-driven prediction. And here you see the accuracy. So we see that for this problem, the DDSP has accuracy that is not that much lower than SP, but it's 70 times cheaper. And the superparameterization, data-driven superparameterization is much better than the parameterized low-resolution model. Here we see that also a DDP does pretty well. It's much better than a physics-based parameterization, although the accuracy is lower than DDSP. And in this problem, even a fully data-driven forecast does pretty well. Now, the problem that we worked with so far had a scale separation. It had temporal scale separation, as I showed you earlier. So going back to those results, just to remind you, this is like an example of time series of X, Y, and Z. And we'll see that there is temporal scale separation between X, Y, and Z. And in a case like this, doing parameterization like this, it's sort of justified. You can assume that there is instantaneous quasi-equilibrium between X and Y. Now, we can change some of those coefficients in the same Lorentz system, keeping F the same. And we can build a system when actually there is not much temporal scale separation between X, Y, and Z. And in a case like this, you don't expect a parameterization like this to be accurate. So now to show you the results, here the red circles, this is basically for the second case, which doesn't have a scale separation. And we'll see that, well, now DDSP is not doing as well as before, but it's sort of close to super parameterized model at a much lower cost. But here, doing machine learning, applying an ANN on the data-driven parameterization, it actually doesn't help. It's even, the results are a little worse than physics-based parameterization and the same as just doing fully data-driven prediction. So here, these results are not surprising because we know that when you do super parameterization, we are solving for the equations, we account for the transient response in the smallest scales. And so it's not surprising that when we reduce the scale separation, the results are much better compared to before between the DDSP and DDP. So I think here there are some promises in this data-driven superparameterization approach. And I'll talk about some of the challenges at the end. But let's talk about generalization a little bit. So far, everything that I showed you, the results were trained with data from F equals 20, and it was tested on data from F equals 20. Now we can increase the forcing to F24. The system would become more chaotic if you just do training and testing on F24. We see that generally prediction is harder. Now we can see what happens if we now train the data-driven methods on data from system of F equals 20 and apply them to the system that has F equals 24. We'll see that DDP and DDSP, which are both hybrid models, they are numerical and data-driven together, they actually seem to generalize, like you kind of can reach the accuracy if you had F equals 24, F equals 24. But if you look at the fully data-driven method, now there is a big generalization gap here because the data-driven method doesn't know anything about the change in the forcing. And so this shows some of the challenges in relying on fully data-driven approaches when we have this kind of non-stationarity in the data. Now we can look at the second case when we didn't have a scale separation, which generally turned out to be a harder problem. And we see that in this case, even the superparameterization method does not generalize well. So here again, the triangles are when the training is F equals data from F equals 20, and the testing is from F equals 24. DDP seems to be generalizing, but its accuracy was lower to begin with. So we want to see whether there is an easy way to close this generalization gap. And one idea that we looked at is transfer learning, which is something that in the machine learning community has been used for image processing and things like that. You can train on images from a car, and then you want to use it to look at images from a truck, and you can actually make it happen. So the idea of transfer learning is this. What we did so far is from a distribution of data, when the forcing was F equals 20, we took 1 million samples to train an ANN or RNN when it was randomly initialized. We trained it and we found the weights for F equals 20. The idea of transfer learning is that now if you want to find the weights for F equals 24, of course, if you have another 1 million samples, you can do it. But let's say we may not have that much data, but we might have a little data. For example, maybe we have 10,000 samples, 1% of what we have. Use this new amount of data, this 10,000 samples from the new system, and retrain your ANN or RNN, but do not start from randomly initialized weights. Start from the weights that you had already found. And so this is basically the idea of transfer learning. So we can do that and find the weights for f equals 24. Again, the advantage is I don't need a lot of data. I can just use a small amount of data from the new system. To see how this works, well, here the stars are from the transfer learning with only 1% of data from the new system. And we'll see that for both fully data-driven and for DDSP, we can close the generalization gap, and the accuracy is now as good as if we had 1 million samples from f equals 24. Now to summarize, DDSP, it shows promising results in this simple model in terms of its accuracy is comparable to superparameterization, and its cost is pretty low comparable to a parameterized low resolution model or data-driven parameterization. And regarding generalization, transfer learning can help with closing the generalization gap with a very small amount of data from the new system. Now, in terms of, and as I mentioned before, these results for the Lorentz system are all in this paper that is on arXiv. Now, of course, in scaling this up to more complicated systems, if better climate modeling is the ultimate goal, there might be some challenges. One is to be able to do data-driven integration of the equations for the smallest scales. Now here we used an RNN as we look at more complicated systems that are turbulent and two-dimensional, three-dimensional, using convolutional methods or even RNNs and CNNs combined. People have found some promising results with them. And so I think there is a chance that that would work and allow us to scale up. The bigger problem that we expect is to face numerical instabilities in hybrid models when we do online testing. This is a problem that for DDP, for data-driven parameterization using machine learning, many people are now finding whether they are looking at ocean models or parameterization for moist convection. We train a data-driven model using, for example, CNN or an ANN, and it works very well in the offline mode. But then when we couple it with a numerical model, the hybrid model blows up. And so people go and try to do a lot of things like killing backscattering or decreasing the feedback and things like that to stabilize the model, but then you lose all the accuracy that you have gained from doing machine learning. So I think this is one of the challenges that we might face. We didn't have this challenge in dealing with the Lorentz system, but again, going forward, I think this would be one of the challenges. And I should mention that we have a postdoc position to work on some of these ideas. So if you are interested or if you know somebody interested, send me an email. So that's pretty much it. One thing I should mention is that everything we did so far with machine learning was deterministic parameterization. And of course, stochastic parameterization is something we know that can be helpful. And I understand that the next talk would touch on that. So I'll just stop here. Thank you.
Thank you very much, Pedram. I guess we have time for some questions. So anyone who would like to ask something?
I have a question.
Oh, yes, please go ahead.
Me? Yeah, okay. Hey, thanks very much, Pedram. It was a very nice talk. I have a couple of questions. The first one was when you described the reservoir computing and you showed you had a forecast horizon of 2 time units, the Lyapunov of time units. Out of interest, have you tried running the reservoir without, I mean, just as a random feature map without those internal dynamics? By any chance?
What do you mean, like without what part of this? What part?
Well, the reservoir you feed in, your output, your input with some parameter matrix acting on some input plus some other parameter matrix on. Oh, here you go. If you ignore the internal dynamics. So if you ignore if A is 0.
Okay, we haven't done that. We just assume it wouldn't work because that's, we haven't done that because so in reservoir computing, the input layer and A, these are randomly chosen and fixed. They're not trained. And only the output layer is trained. basically if A is 0, well, if A is 0, then you don't have anything from the state, right? So R is the
No,
state.
no, it's called random feature maps. It's sort of a very small, very, very simple way of machining. But thanks, that's
okay.
That's it.
Yeah, we haven't done that. Yeah.
Thanks. Yeah. And then for the, you showed these plots like around page, I think it was 14 or 15, but maybe I got that wrong. Where you should, yeah, those ones, for example. Do you have any error bars there? Like, I mean, depending on how you choose the parameters, you know, the parameters in your reservoir, I mean, there's quite a bit of spread in my experience.
Yeah, so, and the output is pretty non-Gaussian. And we try to put the error bars like 25, 75% or something, and things become very messy. But we did a U-test between these because each of these are from with 100 initial conditions. And we did a U-test, and most of these points are like the difference is statistically significant, like the ones that matter at least, like when you are looking at, I don't know, like here, for example, DDSP versus this, the difference is statistically significant. But yes, there is a spread.
Does it change from method to method? Does the spread change depending on the method you're using? Or
yes.
is it roughly the same order?
Another thing we found again is that it has long tails. It has like a Pareto distribution. And it's something that we are actually interested in looking into. But again, just putting the confidence intervals or something on the figures, we found it to make things very hard to see. But we did a U-test just to see the statistical difference.
Okay. Thank you very
but
much.
I would be interested in chatting more about like what comes out of these methods. It's not just the reservoir computing, even like GRU and LSTM, they all do that.
Well, thanks very much. Yeah.
And I have one quick one. So when you are saying the computational complexity is going to be reduced when you're using these neural networks, right? Are you talking about the computational complexity just to evaluate this neural network-based approximation of your P? Is that what you're talking about?
So, I mean, ultimately, I'm talking about reducing the wall clock time on a cluster. And I think that's eventually how we should report the computational cost of these methods. Because when we do DDSP, we are not even finding any P or anything. We are just, we are integrating these equations rather than doing numerical integration. We are just doing data-driven integration.
Yeah, but it's still like a function evaluation there, right? I mean, in my experience is that, you know, you let's say you propose a particular neural networks, and then there's a width, there's a number of parameters. Let's forget, I mean, you say, let's ignore the learning. Let's just say you already have the parameter.
Yeah. So
every time you have X, you have to evaluate that. So there is a computational complexity going over layer. So
for sure.
Of course, in a wall clock time right now, we have a very smart computer to basically parallelize all this probably. But in terms of complexity, I still feel like, I mean, probably, I don't know, like compared to super parameterization, is there any particular, I think the complexity should not be, you know, they should be about the same, right?
Machine learning methods, when it's trained, then everything is for just for matrix multiplication. And there are many things that can be done. For example, when the network is big, you have a lot of weights. Many of them are near zero. So there is like pruning you can do. You can like kind of reduce the size of the network. And we didn't want to get to any of those because there's also like issues of transferring data between CPUs and GPUs when you are doing this. So we use this very simple, admittedly, a simple measure of cost.
No, I understand. But in terms of actual like numerical analysis, computational complexity, I'm not sure actually the neural network is actually cheaper than, because the number of function evaluation could be big anyway, you know, right? So, but in your metric, I understand your metric. Thank you.
Thanks.
I had a quick question. So in the super parameterized formulation, so we assume that we know the equation for the x's. Is that so? So the equation for the x's, we know it, or we can solve it by DNS. And do we assume also that we know how the y's and the z's feed into the x equation, or we only train on some type of residual in the time tendency? I didn't quite get that part.
Yeah, that's a good question. So, I mean, first of all, I should mention here we completely ignored z. Okay, although it could also be parameterized and we could play games with it, but we ignored z. Now, in the numerical superparameterization framework, you need to know the equations, right? In data-driven superparameterization, if you know the equations, you are just reducing the cost. But also, I can see that you might have a case that you even do not have the equation. So still, you just use this data-driven approach, learning from some data that might be available from observation or something, and just find something about the tendency that the smallest scales would fit back into the equations for X. But for now, the way that we see it is if you can really take a superparameterized model, then we know all the equations and just reduce the cost by doing the cloud resolving part data-drivenly.
Mm-hmm. So but I
Dimitri, guess. Oh, sorry. Continue.
Well, so then I guess, which is fine. I mean, you use you have to use high resolution, high fidelity training data, basically from the full model.
For sure.
So you have like a one-time like offline cost to generate the high fidelity training data, but then you can run with it significantly cheaper.
Yeah. Yeah, and because of that, we started thinking about this transfer learning because we don't want to have high fidelity data for every forcing that we are going to apply to the system. And again, in that sense, transfer learning can be useful because you need to have a lot of high fidelity data to do the training and then to do generalization, to look at, as you change some of the parameters of the system, the transfer learning can help because you will need a much smaller amount of high fidelity data.
Vasily, one last question.
Yeah, just quickly. Thanks, Pedram. That was great. Nice introduction. It's to the whole field. Means I don't need to cover it in my talk, so I appreciate that. And also just about a comment on how superparameterizations work in large-scale systems. It's my understanding anyway that typically there are certain sites that are cherry-picked or intelligently selected where you run the higher resolution, higher fidelity convection resolving code locally, and then there's some relationship determined between the large scales in the GCM in that one box and the high fidelity model run within that box, and then the relationship is applied more broadly. So there's only a one-way coupling to the high fidelity. The high fidelity model knows about the large scale features that are kind of uses boundary conditions, and then all the details are filled in, and then that relationship, if you like, the coarse-grained version of the high fidelity model, how that differs from the GCM result, that relationship is then applied more broadly. In the large scale system, that's generally how it works. Is that your understanding?
So I think there are at least two superparameterized climate SPCAM and now E3SM. So those models actually do superparameterization for every grid point. So,
but surely they're not running a high resolution version in every grid cell of a GCM.
They do.
Really?
So they don't do 3D, but they run a 2D CRM, cloud resolving model. And that's why SPCAM is much more expensive than CAM. But then it captures MJO, it does a lot of other things. But what you are describing, what I've seen is I think that's what Clima project, for example, is trying to do, to selectively, for ocean and for atmosphere, do some of the LES simulations, learn the relationship, apply it everywhere. But as far as I know, SPCAM and E3SM, they do this for every grid point. They don't do 3D, but they just make it 2D, so it would be cheaper. But the whole model is much more expensive.
Sure.
I think we should move on to the next talk. Let's thank Pedram again for the very nice talk.